The well-known Hubble telescope observes astronomical objects in the ultraviolet, visible, and near-infrared regions of the electromagnetic spectrum. However, many aspects of space can only be observed with telescopes at different wavelengths, such as X-rays. The Chandra X-Ray Observatory, NASA's flagship mission for X-ray astronomy, is one such space telescope. The Chandra Source Catalog holds images of objects such as exploded stars, galaxies, clusters of galaxies, and matter around black holes. Just to give you an idea of the data, here are some images of the NGC 3079 galaxy in the visible light, in X-ray, and the composite image that you're used to seeing in the news. And finally, here is an image of Abell 1033 galaxy cluster. Interestingly, the composite of the optical, the radio, and the X-ray image combine to create something that looks mysteriously like the Starship Enterprise from Star Trek. The standard file format for astronomical data is a .fits file. The major data is collected in what are called events. The event file stores photon event data as a table. However, JPEG files are also available. The Chandra Chaser tool was used to query specific object types, galaxy or cluster, and specific product types, JPEG files. The dataset used for this project was manually obtained and can be downloaded from this box link in the description below the video. All code for this project was written in Python with TensorFlow backend on a MacBook Pro 2.6 GHz Intel Core i7 with 16 GB memory. The validity of the project and results were monitored and verified by an engineer and astrophysicist at the Harvard-Smithsonian Center for Astrophysics. Each model is defined, compiled, trained, and then tested on unseen data. After loading in the necessary libraries and reading in the images, you can see that we have approximately 200 images each of galaxy and cluster, 50 each for validation, and about 80 total test images. This is not the ideal train-validation split and should be modified when more data is obtained. The first step is to examine the data. Here you see the colorized, zoomed-in images from the Chandra photo album for the Whirlpool and the NGC 3079 galaxies, and the raw images in our dataset in grayscale. And here are the galaxy clusters below them. If we zoom in on the NGC 3079, you can begin to see the important features such as the superbubbles and the black hole. To build the models, you first need to create generators for train, validation, and test with image data generator and flow from directory, while rescaling the images at this time. Model 1 is a 2-layer CNN with about 155,000 parameters to train using images scaled to 32 by 32. I'll define the model here and then compile with the Atom Optimizer, which seems to work best with this dataset. I used Keras callbacks and saved only the best weights across 8 epochs. I ran for more epochs, but hardware resources restricted me to this number for now. Here you can see the model results with a max validation accuracy of about 78%. When exposed to unseen test data, the results were a rather encouraging 79.75%. Below is the count and normalized confusion matrices, so you can see where it is only slightly easier to classify galaxies than clusters. Model 2 uses a larger image, 64 by 64, and 4 ConvNet layers with about 500,000 parameters. The training process is the same, and the validation accuracy, as you can see, is about 77%. On unseen test data, the results are slightly lower at 73%. And here again is the confusion matrix. This model is strongly biased to classifying galaxies correctly. Model 3 adds image augmentation, specifically ZCA whitening, which is a linear transformation of an image that reduces the redundancy in the matrix of the pixel images. With less redundancy in the image, the learning algorithm can better highlight the structures and features. This time you'll use a different function to create the training generator, while leaving the test and validations the same. Everything else in Model 3 is the same, and here you see the validation accuracy results. The test accuracy is again in the same range at 76%. Model 4 uses L2 regularization on the smaller model defined for Model 1, except you'll use RMS prop as the optimizer during compile. Max validation accuracy here is 78%, and test accuracy is 78%, which yield the most stable and consistent model of all. The average validation accuracy and test accuracy percentage is in the upper 70s across all models, reaching as high as 80%. Finally, feature visualization is used to show important features via intermediate activations. Using Model 2, the Whirlpool Galaxy and the Abell 1995 Galaxy Cluster, you can see that the first layer is retaining the full shape of the galaxy or cluster. At this stage, the activations retain almost all of the information present in the initial picture. As we go deeper in the layers, the activations become more abstract and less interpretable. They begin to encode higher-level concepts such as single borders and angles. Higher levels of the model carry increasingly less information about the visual contents of the image, and increasingly more information related to the class of the image. It almost seems as though the most visible stars appear as important features in the galaxies, and the same for galaxies within the clusters. This could potentially be a way of identifying prominent sources within observations. A few lessons learned are: the CNNs used in this project were able to obtain a test accuracy averaging near 75%, which shows promise for the use of deep learning in astronomical source classification. To be used in practice by astronomers, astrophysicists, there will need to be many more images than what was used in this project, with considerations given to the type of files used as inputs. Larger CNNs did not perform better than the smaller two-layer models. More epochs should be tested, but they seem to level out after only a few. The train validation dataset split should be improved. Currently, it is more of a 50-50 split versus an 80-20 split. This was because of the complexities in moving the images around. As a result, the validation accuracy always started out higher than the train accuracy. there is an opportunity for more hyperparameter configuration, such as learning rate. The results in this project are encouraging and indicate there's a potential for deep neural nets to classify other astronomical objects beyond just galaxies and clusters. The challenges are mostly around the data itself, but many opportunities involve adding non-image type data to the models. The next steps for this project would be to substantially increase the dataset size and to add different types of objects to the classification categories. I've enjoyed working on this project and collaborating with resources at the Smithsonian Astrophysical Observatory and look forward to ongoing work. Deep learning in astronomy is needed to examine and classify a continual stream of data obtained from space telescopes, and this project has shown its potential. As I mentioned before, there are many different types of X-ray or visible or radio or infrared type images that could be examined using deep learning techniques. A lot of opportunities exist. Take a look at some of these different images now. Thanks for listening.